Good morning, everyone. I warmly welcome all the participants, esteemed speakers of the day, trustees of VES, faculty members, students, architects, on the third day of webinar, Alternative Construction Technologies. Before we begin with the event, as a part of VES tradition, I would request everyone to join me chanting Om 3 times. Om. 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 Thank you. The theme for the fourth webinar series is Alternative Construction Technologies. The webinar is an approach to understand paradigms of design and build practice. Day one of the webinars, we interacted with architect Girish Doshi sir and Professor Sankalpa, who elaborated upon the emerging construction technologies in Indian context. On day two, we interacted with architect Dean De Cruz and architect Manak Singh, who elaborated upon the sustainable techniques involved in developing climate responsive architecture. With this, I would like to invite our moderator of the day, Professor Abhijit, to take over and continue in introducing the speakers of the day. Thank you.
Thank you, Pulkit sir. Good morning, everyone. I welcome everyone to this webinar, all the guests and participants in this meet. We also have about 80 to 100 VESCO students who are attending this webinar live on YouTube. A warm welcome to all of you. I would now like to introduce our first guest speaker for the day. Architect Satprem Maini sir is a French postgraduate architect in earth architecture, and he has lived in Auroville, India since 1989. He is the founding director of the Auroville Earth Institute, where he works as an architect, a builder, consultant, researcher, trainer, and lecturer. He has worked in 36 countries and with his team has trained over 13,500 people from 91 countries on earth architecture. Satprem sir is the representative for Asia of the UNESCO Chair Earth Architecture, Construction Cultures and Sustainable Development. He has been granted 15 awards, 4 international awards and 11 national awards. With this, we welcome architect Satprem sir to the dais and request him to begin with his presentation.
Thank you, Abhijit. Welcome, everyone. I will start my presentation. As you can hear, and you know, I'm French, and I cannot lose my French accent, sorry. So I hope you can follow what I will be saying. This will be the summary of the presentation. I will start first with the paradigm of modern architecture and sustainable development. I will go on with urban architecture in the world with a brief introduction of a millennia-old tradition. Then we'll see an introduction on CSEB, compressed stabilized earth blocks, research and development that we do here. And we'll finish with a selected project with that we have built and some data. And in fact, sorry, I go too fast, and a few examples of CSEB in the world and some data. So paradigm of modern architecture, modern cities, they are looking all the same. This is Cairo with horizontal development. This is New York with vertical development. This can be, this one can be Mumbai, Delhi. This also can be Chennai or Delhi or Mumbai. You have this everywhere in the world. This is in Boston, the City Hall from the 1968, 1970s. How many tons of concrete is in this building? And how much initial embodied energy also? And how much carbon emissions? There was at the time a project of rehabilitation, and they proposed this. That means, again, more energy hogging materials and technologies. That means more embodied energies and more carbon emissions. So as we speak of embodied energy, we should define what it is because not everybody knows that. So first we have to speak of initial embodied energy, which is non-renewable energy consumed for the construction, for the acquisition of raw materials, their processing, manufacturing, and transportation to site. That means it's the total amount of energy you have to consume from A to Z, from the quarry, if you want, till the end user. It is in general a good indicator for the environmental friendliness of the buildings. The initial embodied energy can be about 30% of the energy consumed for the building during its lifetime. That means when you speak of green buildings, I will come back after on that. They can save a lot of energy in their operation use, but they will not deal with that. I will come back after on this. Now we have the recurring embodied energy, which is the energy that you have to consume to maintain, to repair, restore, or refurbish or replace materials during the lifetime of the building. And then you have operating energy, which is how much energy you spend for heating, cooling, ventilation, lighting, and so on. So, example of carbon emissions and embodied energy. We have here aluminium, one of the highest. Of course, these numbers they cannot give you. This is megajoule per cubic meter, kilo of CO2 per cubic meter. And then compared to steel, about 3 times less, 2.5 times less. Then you have toughened glass, 10 times less. Concrete fabrics, 100 times less. Reinforced concrete, less. Then we go to plain concrete and to CSEB. You can see the difference here. Of course, we cannot build everything with CSEB or aluminum, but you can see the difference in energy and carbon emissions here. Example here of lead platinum, building in Tel Aviv. How many tons of, how many tons of carbon emissions and embodied energy in this building? Because one of the problems with LEED accreditation, they don't take into account the embodied energy. They just deal with operating energy here. So that means they want to have the minimum energy consumed for the use of the building, but they don't deal with embodied energy. And when you know that 30% of this consumption is the embodied energy, it's not possible not to deal with that. Especially when buildings like this can consume less energy for their operation, this could jump even higher, like 40 or 50% of the energy for the embodied energy. That's why when you want to design something with whatever you want, you have to think of a material which can have much less embodied energy into the building. Now, example of the concrete industry and the cities. Cities, they take about 2% of the Earth's land surface, but they consume 75% of the natural resources. That means there is really a big imbalance here. The construction sector is responsible for about 40% of the consumer resources, 40% of CO2 emissions, and also 40% of waste from construction and demolition. Now the concrete industry. You see, buildings account for about 30 to 40% of the total global usage. Now concrete. 1 ton of cement consumes about and emits about 0.95 tons of CO2. 1 ton of concrete emits 0.0107. Because concrete here will have aggregates inside. There will be sand and gravel inside. And the cement production accounts for 5% of the global CO2 emissions. And even some people say it's much more than that, like 7 to 9%. Example now with emissions by burning wood for the country fabrics, which are produced in the south of India, like in Tamil Nadu and Pondicherry. So this is what they do in Pondicherry area. They do clam kilns like this with a lot of wood inside. In the past, they were burning 100 tons of wood for 1 acre of bricks. Now they burn about 50 tons only. So they have reduced the wood consumption, but still it is a lot of energy consumed. An example, wood combustion. 1 kilo of food contains about 440 grams of carbon. And when you burn it, you have emission of 3.6 kilos of CO2. And this is the kilos of CO2 for 1 kilo of wood burnt. That means you have more emissions than the weight of the wood, you can see. So now if you have a general data for this, you have 50 tons of wood will emit about 79.2 tons of CO2. And will burn this much of energy, 750,000 megajoules. So these are not small amounts. And when you go to the north of India, where they burn fabrics with coal, it's even worse, maybe, because you have this kind of data. You had in 2016, 200 billion bricks produced in India, which is the second largest producer after China. This was 35 million of tons of coal burned per year. And coal combustion, some data again for that. When coal emits much more than wood, you can see wood was 1.45 kilos of CO2 per kilo of wood. And here you have 2.285 kilos of CO2 for 1 kilo of coal. That means much worse emissions with coal than wood. And in terms of global data, you have 35 million tons of coal burnt annually emits this much of CO2, 79,970 million tons of CO2. And this goes into the atmosphere and the lungs of people also, and consumes 840 billion megajoules. These are too many zeros to imagine what it can be. Now we speak about sustainability because everybody speaks about it, but we don't really know what it is and we don't practice it also. Definition from the World Commission. Sustainable development is development which meets the needs of the present without compromising the ability of the future generations to meet their own needs. That means whatever we do today, we should allow our children to do the same later on. And this is not the case. Wisdom from the past, which is from Kenya. No, first, I got too fast, sorry. I go first to the Upanishad. All in this manifest world, consisting of moving and non-moving, are governed by the Lord. Uses resources with restraint, do not grab the properties of others, distant and yet to come. So this speaks of equity here, of course, but also of control of resources from nature. That means if you don't take too much from nature, you can leave something for your children later. And now Kenyan proverb, treat the earth well. It was not given to you by your parents. It was loaned to you by your children, which speaks about the same than this. You see, here we speak of preserving the resources for the future generations. And here they say that the children, they loan our land. I see different dimensions of sustainability. We have 3 dimensions here. Social, which is to uplift the local skills, empower people. Then to environmental, which is to properly manage resources from nature, of course. This, in fact, this is the first step to do if you want to do something in the world now. And then finally, economic, which is to promote endogenous growth. It means local growth. So examples of architecture in the world. So this is a map which shows the different constructions with earth in the world. You can see almost every continent has earth construction. In fact, all the continents, apart from the very Nordic areas where you have just snow, you don't have earth construction, but of course, no buildings like this in the forests of Amazonia. But you can see also all these dots here. These are the UNESCO World Heritage Sites, and you have 112. So first, we'll see the statistics from UNCHS Habitat. They said once that 50% of the world population lives in urban buildings. That means about 3 billion people. 25% of the world population does not have access to decent housing. And UNESCO states 17% of the world cultural heritage is built with earth. 25% of the World Heritage Indenture is also built with earth. And 14% of the 100 most endangered World Heritage sites is also built with earth. So these are not small amounts. So here you have 112 heritage sites in the world. In India, we don't have, unfortunately, though there could be some, because you have beautiful examples in Goa, in the north of the Himalayas also here. We'll see some photos later. Examples here, this is Tabo in Spiti Valley, Tabo Monastery, which is 1024 years this year. You have here Tibet, you have here Morocco, Shibam. With the mountain, Shibam is called the Manhattan of the desert, because you have up to 8 floors high buildings, 30-meter tall buildings just with mud, nothing else than pure earth. A chateau in France, here you have Ramesseum in Egypt, the oldest building with earth still standing, 3,300 years old, more or less. What are CSEB? They are a mix of soil, sand, and often a stabilizer, often cement, with 5% only inside and some water. They are compressed in a press, which can be manual or motorized, and cure for 28 days if you have cement. If you have lime, you will have to cure a little bit also, but less than cement. They can reach a dry composite strength of 9 megapascal in Auroville. As an average, we have 6.5 to 7. The topsoil is always removed. We never use topsoil for this technique. We have to remove it and use it for gardens after. CSEB are used on all continents. They have been, for me, a major tool for the renaissance of architecture in the world. Because there was a big decline in the 1950s, and today people are building again with earth. And this technique of CSEB has been a tool for that. So this is what we use the most in Auroville and also in the world. The first manual press for block making was called the Sinvaram, developed in Colombia in the 1950s. And this press has been copied a lot, and many presses are today available. We became one of the leaders in this field. We have created a full range of equipment for building with earth called ORAM. So the ORAM press 3000, which is a manual press, can produce about 70 different types of blocks with 18 molds. You can have many options for whatever your needs are. We have a very high precision with the block making, maximum 1 millimeter is, of course, if the workers are careful. Examples of machine in the world, you have here the Sinvaram machine, the first machine produced in Colombia in the 1950s, a small machine from Belgium, one from India, which is not produced anymore, machine from Belgium again, this is ORAM press from Auroville, and then motorized machines from different places of the world. Now we'll see some characteristics of CSEB with 5% cement. Dry composite strength 5 to 9 megapascal. Weight 3 to 4. That means more or less half. You can see that even stabilized with some cement, the earth block will reduce in strength. Because even wet, the block will be slightly weaker. It will still be resistant because if you have pure earth, wet strength of earth blocks will be earth block without any stabilizer, it will be 0 if it is wet. But if you have cement, it is slightly lower than the dry strength. Then dry bending strength much less, 0.5 to 1 megapascal only. But normally you don't have bending in a building. If a building is well designed, you don't have bending. So this is not an issue at all. Dry shear strength 0.4 to 0.6 megapascal. This is a minimum. And you can have shear in the building in an earthquake, for example, or if the building is not well designed. Because if you don't have a proper design, you can't create shear in the building. That means this can be avoided if you have a proper design. Water absorption, relatively less compared to fire bricks, 8 to 12%. Apparent bulk density is quite heavy compared to fire bricks. In Auroville, we have about 950 kilos per cubic meter for this. Embodied energy we have seen, 11.2 times less. I will come back on that at the end. And carbon emissions about 13 times less than country fire bricks. 1 megapascal is about little more than 10 kilos per centimeter square. These data are from Auroville after 28 days of curing. And these characteristics are influenced by, of course, first the soil quality, then the compression ratio of the machine and its force. Of course, the quality of manufacturing and especially the curing, because if you don't cure the blocks, because as you have cement, you have to keep the blocks humid for 4 weeks, then you have a proper strength with that. And of course, the quality and percentage of stabilizer, if it is cement or lime and how much you have inside. Indian standards, we have a few standards in India. This is what we have. This was first done by Gujarat state after the earthquake of Gujarat in 2001. They have approved our technique for CSEB, for the reconstruction of Gujarat after the earthquake. This is the official standard from India on the stabilized soil block. They call it stabilized soil block. They don't call them CSEB, but stabilized soil block, but it's the same. They have as a standard like in Sri Lanka. In Nepal, they have also manuals which are approved by the government for the earthquake resistance, especially with CSEB also. So now we'll present our institute. Just a brief introduction to see what we are doing. We were founded in 1989 by HUTCO. We have the representation for Asia of the UNESCO share of architecture. We are a member of a world network. We have received 15 awards for international and 11 Indian awards. We have been finalists for 2 other awards, the World Habitat Award in 2000 and the Icahn Award in 2007. Our activities are mostly training and education, applied research, publications that we can sell, consultancy, construction worldwide, and heritage conservation. But our main activities are these 2 here, training and applied research. We research, develop, and promote and transfer earth-based technology in the world. Training courses activities. We are doing a lot of training courses per year, about 20 weeks of training courses per year, every year. We have trained more than that. In fact, this is not updated because we have more than 13,500 now in 91 countries. And we have, in general, 1/6 of foreigners coming to our place. And now we conduct online courses because with the pandemic, we cannot have training courses conducted in Auroville. So what we do now, we have online courses. And these days, we have 84 trainees from Syria attending our courses online. So this starts to work really well. Of course, these online courses cannot replace the training course in Auroville because you cannot have any particular course, which is really essential if you want to build with us, but at least you can get all the theory with that. Examples of the machine that we developed in Auroville, the manual press Oram 3000 here, a motorized crusher here, a mixer and a press motorized. This is done in collaboration with Oreca, a workshop in Auroville. The blocks that we can do with one machine, this is a machine 3000. You can have the solid blocks here, also solid block with square shape, with a full size block, 3/4 block, half block, rectangular shape, full size, 3/4 and half. You can have also hollow blocks here. with again full size, 3/4 and half, full size, 3/4 and a half, and so on. Earthquake resistant blocks, which are called hollow interlocking blocks. They have some keys here to interlock in each other. We have special blocks like Hodi here, also floors on the roofs. And you have many other blocks like the round box for columns. This will have some reinforcements inside with a little concrete inside. But this saves a lot of concrete and steel compared to a normal RCC column. And then many different blocks, like U-blocks here for casting concrete ring beams inside. Inside here to have pipes inside the wall, on the side of the wall, coping blocks here, coping blocks here, flashing block here, tiles for the floors also, only 1 inch thick here. So this is block making by the press manual.
The earth is mixed.
Okay, so now we have here 200 liters of soil, one third of bag of cement, and 30 liters of sand. We mix it by hand first, dry. So we mix it 2 times dry, then we add some water. Mix it again 2 or 3 times wet. Then fill the soil into the press. The mix goes into the mold. Level it with the hopper, close it. You press here with 2 people. Every time they press here, they give 15 tons on the machine. Then the machine opens. Block is pulled out outside. So this is a device to take the strength of the block initially. So you can see the penetrometer goes back 1 mm maximum. The worldwide standard is 6 mm. You see this height here is 6 mm. Normally, the penetrometer can go by 6 mm into the block, but here it goes by 6 mm. It goes only by 1 mm inside because it is well compressed. After that, the block will be moved on the side of the press. You will see the machine now, and the block is moved on the side. After the stacking, they will be covered with a plastic sheet for 2 days, and then moved outside for 4 weeks of curing. So after 2 days, they will be stacked like this in a big pile and watered for 3 times a day for 4 weeks, because the block must never dry for 4 weeks. And after that, they can be used for building. Now, the block making with the motorized press. So here we have the sand on one side, a partition plate here to control how much sand you put in and how much soil you have. Then the soil. We have here 85% of soil and 20% and 15% of sand. On the front, we have another hopper with cement. The cement flows on the belt. You can see this is to control the amount of cement coming on the belt. So this is for 5% cement, soil is coming here. Now we adjust water on the side here. Water will be spread into the drum. Initially, the soil is not with the correct moisture content. You can see initially it is either too dry or too wet. That's why we have to move it on the side. And this will be put again into the mixer after. So now the mix is okay. The worker sends it on the belt conveyor to the press. The worker here will move it on the side and put it back into the mixer. It's not wasted. And then the soil goes to the machine. You can see now. So this machine is semi-automated press, which has this output per day, about 350 blocks per hour, giving about 2,500, 2,700 blocks per day. We have a bigger machine now, which can produce up to 600 blocks per hour. Control of the strength with the pocket penetrometer. You can see here again, it does not go in because it's really well compressed. Stacking the blocks on the pallet. We have here a trail on the pallet. When the pallet is finished, you move it on the other end of the block yard. It will be wrapped in a film to avoid the water evaporation, but also to help the pallet to be more move easily with the forklift. We put some water on the top of the pile to have a better saturation of water initially. then wrap it completely with a plastic sheet, and then the pallet is moved after with a forklift outside. A different solution is to have the block stacked on the ground, like here. So this will need more labor, but less machines, because you don't see the forklift and pallet now, but you have to take more labor for that now. So now a block in water, because often when we build with earth, people they say, but what about water resistance with earth? So we have a small test here to show the strength of the block in water. This block in water since about 1 hour only.
This block is in water since 2
hours only. So we just claim on it to see the strength of the block. So this block is in water since the 5th of April 95. That means 25 years, 6 months, and today was 17th and 12 days, always in water. Of course, it's not a composite test to show the strength of the block, but this marks the amount of people to show that earth blocks with a little cement inside can resist water. If you had a pure raw earth inside, so it means pure mud block inside, it will be totally dissolved with water. But with 5% cement, it can resist water. Now we'll see some this resistance with CSEB that we have done. We have developed a reinforced masonry system with CSEB, which are interlocking. We have built this house in Delhi in 66 hours. You can see here, this was built in this time. The house was prefabricated in Auroville, transported to Delhi in 1 truck, and then built in less than a week. We have built another house in Gujarat after the earthquake in 62 hours. And this was the starting point of the reconstruction after the earthquake. Then we have built another one in Istanbul for the city summit habitat in 1 week. And this one has a dome. And we have here another house which was resistant for the tsunami, built in Tamil Nadu after the tsunami. Example of the work in Gujarat after the earthquake. This was the work done with the Catholic Relief Services that we have assisted. Because our team worked maybe 6 months totally in Gujarat to give training courses, different evaluations, advice, and consultancy. And then we helped this organization to build so many houses, 2,698 houses built in 1 year in certain villages with 2,000 people. And this was a very good example of totally adapted answers to the earthquake. Because they didn't build mass housing, but you can see here they have built 10 houses here, they have built 1 here, 10 or 3 here, totally in the ruins on the land of people, instead of the ruins of their house. We have government approval for this, first from Gujarat, after the earthquake of 2001, then from BAM, after the earthquake of 2003 in Iran. We can also build up to 2 floors. And finally, from Tamil Nadu after the tsunami. Because the requirements for the tsunami and the earthquake resistance are quite the same. We have some training manuals that we publish in Auroville. So this is our code of practice for the CSEB. That can be sold if you want. The earthquake resistant manual. Manual for arches, vault, and domes. And another one with all our recipes for the different ratios of different techniques. So now examples of buildings that we have done in Auroville and elsewhere in the world. The visitor centers that are built with Suhasini Iyer from 1989 to 1992. We received this award in 1992 here. So this is access to the boutique of Auroville. So archers everywhere here. So this is our training center and our office. This is the office below. This is my house above here. We have CSEB everywhere. a school in Pondicherry, Shakti Vihar, for 1,800 children. There are 24 classrooms of this type here in this school. The school is used day and night because they have day classes and they have night classes for kids, for elder kids. Vikas apartments on 2 floors in Auroville in 92. 4 apartments only on 2 floors. We have, in fact, we have an arch here as an overhang, but we have also walls and domes inside. Dome for the square rooms here and wall for the bedroom here. Miramuki or Deepanam School in Auroville, built with stabilized rounders. The walls are done with stabilized rounders. That means there is 5% cement in the earth also with some sand, which is rammed in situ. That means we have a formwork and we ram by layers inside. We have domes. This pyramid here is just to cover a dome. There is a dome below here. A big vault of this school, deep, so 10.35 meters span, built in 3 weeks. So you have here 17.7, 17.7 centimeters at the base, 14 here till here, and again 17.7 on this side. Built in 3 weeks without any support. I cannot explain everything now because we have a short time, but if you want, you can see our own course, our online courses and come later to our center to be trained. So this was built without any formwork. Because apartments on 3 floors now, on 4 floors, really, you have here a basement floor plus 3 floors above. So 1, 2, 3, 4 floors, entirely covered with walls here for the bedrooms and dome for the living room here. The Temple of the Dalai in Kombato. So this was not built with CSEB because we did not have time to produce the blocks because it was built with fabrics here. But it was built in 9 weeks. That's why the guru was in a hurry to build this dome. This is a guru, Jaggi. He was in a hurry to build the dome. That's why we could not have time to produce blocks locally. And we had to build it with fabrics. And this was really a trouble for us. It was really not easy to use this material. Because they're not strong enough, they're not accurate enough, and it was really difficult to build with them. But we could do it in 9 weeks. So this was the result after 9 weeks of work. A small house with Strobel and CSEB. We have here a frame structure with CSEB, not RCC. You have a frame structure with CSEB column here, CSEB column also here, CSEB wall here, CSEB column here, and then the filler walls are with Strobel, with the lamp plaster. Walls on top with CSEB, dome on top with CSEB, also waterproof with stabilized earth. It was covered later with ceramic tiles. Inside, this is my living room above the office. We have here equilateral vault built in 2000, 3.6 meters span. Equilateral vault because it is within the equilateral triangle. If you see this triangle here, it is equilateral. That's why it is called equilateral vault. The house that we have built in Gujarat after the earthquake is in 62 hours. The house was also precast in Auroville, transported to Gujarat in trucks, and built in less than a week. And after this house was built, people started to work with our technique in Gujarat to rebuild Gujarat. And after this house was done, the government published the guidelines and the standard. A small house here with rounders, stabilized rounders here, and CSEB for the walls, and walls here with CSEB also. Another small building with a dome, a ponto dome here, on CSEB which rests in a pond here. Almeidi Mosque built in the heart of Riyadh in 2004, sorry. So this mosque was built in 7 weeks. It's about 420 square meters with a minaret of 18.05 meters high here, entirely covered with walls and domes here, built in a so short time. Inside the dome, inside the mosque finished. Our team only did the rock construction. We did not do the finishes. This was done by the local contractor. So this was with our team. In fact, we had 4 masons from Auroville with the co-director helping me for the training course. And we had to employ about 175 people for this work, masons and laborers. The small pyramid temple of Nataraja near Auroville. So here we have inside a small dome. There is a dome inside with Nataraja inside. A small cloister dome here of 6 meters square here only, very small temple. And this is entirely built with CSEB. A small school near Auroville with a square dome logo. There is a square dome here of 7.5 meters span, square dome here, ferrocement channels here, which is a good alternative to reinforced concrete slabs. CSEB walls everywhere, of course. Composite column, this is a round column. This is 29 centimeter dia with concrete inside. There is only 4 bars of 10 mm inside with a little concrete inside the holes. A school built in Nepal. This was a very important project for us. It was a small project, in fact. Maybe the school was about 100 square meters only, but it was built with people. These people in blue here, they're all villagers. It was built with a community participation because they wanted to have their school built by themselves. In red here, you have the paid masons. And the school was built in 20 days. What we did was to train a team from Nepal in Auroville. So one architect and one engineer came to Auroville to be trained here. They took 1 week of training course. They went back to Nepal. They trained their own team. They produced all the blocks, produced all the ferrocement channels locally. They did the foundations, and then they came to help them to build the superstructure of the building. And from here to here, 20 days. And what was really good for the project also after was that the team of Masons with the local NGO went again in different villages to build the same type of school in about the same time. They have built 3 or 4 schools with different people from the different villages with the same team of Masons, and always in about the same time, always in about 3 weeks of work. A project in Spiti Valley in Casa, the Eco Community Center of Casa, which is earthquake resistant, which has received this award in 2016. Here we have mostly rounders. As I said before, rounders is rammed in a formwork by layers. So here we have only raw earth. We don't have cement into the walls here. We just have a few CSEB here for the cobble here, which protects the trombone. Trombone is a glass wall in front of the rounders wall to have a passive solar heating. And this worked extremely well. I don't know if you know the climate of Spiti, but Spiti can have up to -40 degrees Celsius in winter and up to +40 in summer. This means they can have up to 80 degrees difference from summer to winter in the interim weather case. An example, in 2018, they had -21 outside. In fact, because we had some temperature survey time to time by the local people here, it was 8 o'clock in the morning, -21 degrees outside and +10 inside without heating. In this room here, which is a cafe of the center, at 8 o'clock, there was 10 degrees inside the room and -21 outside. So 31 degrees difference without heating. And in fact, we have not even provide heating system in the building because you just dealt with the trombone. And people, they are, of course, they are used to the cold, so it means 10 degrees for them is quite okay for the living inside. Not for us in Tamil Nadu because we have very hot temperatures here. But for 10 degrees inside, with a wood sweater, people can live comfortably in this building when outside you have -21. And this is because of the thromb wall, which can give passive heating to the building, but also because of the around those walls. If you have concrete, you will be freezing inside. With rounders, you don't freeze. Apartments at Realization in Auroville is a place called Realization in Auroville, built between 2008 to 2012. 3 floors here. Everything with vault and domes. Vaults for the main rooms. Domes. There is domes below here. Domes below here. Vault on the roof here. Another dome is inside here. Plaster with lime, stabilized earth with lime here on the facade here. Sharanam, this is our the last big project we have done in Pondicherry. The Sharanam Development Center. We have used here CSEB and Podos concrete. We'll see after some photos. Podos concrete is a concrete made of earth and cement and lime. I will speak about it later. We have built dormitories for single story for 32 trainees here, double stories with 32 trainees inside here, for four lodges like this, here. And then the conference hall, which has a vault of a 15-meter span. You have 15-meter span here. It's a conical vault. At the end is smaller. The other end is about 6.61 meter span. And it has up to 15 in front and built on Podos concrete walls. Podos concrete, I cannot detail it here because we don't have time for that. It's not the purpose of the seminar. It is made of earth with some cement aggregates, sand, and water. So he have here in general about 25% of earth inside the concrete, and of course much less concrete. And the strength is really high. You had up to 15 megapascal for this concrete, with only 7% of cement inside. If you want to use a normal concrete with just pure cement Portland with aggregates and sand, a good RCC like M20 will be 20 megapascal of strength, but you have about 14% cement inside. And this one with 7% had 15 megapascal. And because you have earth inside, because the earth binds the grains also with clay, that means as you have clay inside, you need to have less cement inside. That means with this kind of technique, we can build easily up to 6 floors with totally load-bearing masonry. So this is a video of the finishing of the wall. We have here a template to give the shape of the wall. We have here a dummy block which will be removed after. We put a string line here. And the mason lays the block below the string line. We have here, if I can come back here. So here you have a mortar based on earth, a little cement inside. You have basically earth, sand, and 7% cement with water, which is very fluid, like a glue. And the masons just take it easily like this. So you see the vault is the vault is conical. You start here at 6.61 meter span on the bottom side, 15 here. It's conical in height also. The rise here is 1.1 meter and 2.5 meters here. It's conical in 2 dimensions. Oh, no, sorry, I went too fast, so I come back. So I'm sorry, I do some mistake with this presentation. So let's come back here. So this was the last stage of the vault construction. The vault took about, I think, 5 weeks to be built, 5 weeks. And the vault is about 90 tons. You can see it built without any formwork. You can see here the steps of the block, because as we have a conical shape, this gives a step in the masonry here, which is in fact very good for the acoustic. But you don't have any problem of echo or reverberation with the acoustic like this because of these steps of the bond pattern. So inside the building finished, the conference hall of the center. Now we'll see examples in the world about different architects in different countries. So this is near Bangalore by Vivekanand. In Bangladesh by Shah. This was done with our machine. It was later on plastered with lime. A small house in France, in the mountains, in fact, because here you can see the pine trees here. That means they have snow in winter. In Mali, very hot climate now. You can see CSEB can be used on all continents in all climates. In Mayotte, a French, small French island between Madagascar and Kenya, the airport of Mayotte. The prefecture of Mayotte also, with stones and CSEB, mixture of stones and CSEB here. Apartments in Mayotte for social housing. In Korea, South Korea, you can see you have many different styles. You can do whatever you want with this technique and with this material. So now some data on earth architecture. First, thermal characteristics. So here I have hydrothermal behavior. It's important for me to emphasize this because earth blocks have a different, and earth in general, they have a different behavior than other materials. Example here, when you have exposed earthen walls, they have a different behavior because the clay is not burnt, it's just stabilized. That means it can still absorb and release moisture. If you have burnt bricks, the burnt bricks will be, the clay is dead inside. We will just deal with the porosity of the material, but not with the clay inside. This phenomenon is called latent heat. This happens because of the difference of temperature and moisture between outside and inside. And this is happening from day to night and from season to season. Example, outside temperature is higher, the wall will evaporate moisture. That means this will cool down the building. Then temperature is lower outside, the wall will condense moisture. That means this will create heat in the building. And because of that, you have a better regulation of the temperature in the building. This is more effective in temperate climates than tropical climates. Still, in Auroville, where you have a tropical monsoon climate, it is working also. But it will be better it's better in France, for example, or in Spiti also. Even if Spiti is very extreme climate, it works really well. As I mentioned before, in Spiti, in Casa, outside it was minus 21 degrees Celsius at 8 a.m. in the morning, and inside plus 10, without hitting the building. And this is because of the ramdrels and the trombone. That means you don't need to have air conditioning. And you have much less operating energy also. Cost effectiveness. We have to differentiate here cost effective and low cost, because low cost is not always, in fact, cost effective is not always low cost. What we mean by cost effective is to have to spend the money locally, of course, with a minimum amount, but locally. Today, CSEB are costlier than cubic meters than country fabrics. This is today in 2020, but in 2011 it was cheaper by 10%. And for example, the fabrics today are more or less the same cost than in 2011. There will be around what 5.75 rupees a brick, 1 hour around 5 rupees in 2011. But locally in Pondicherry, there is about 70% inflation rate in this area. Of course, our blocks are cost short today because of the cost of the labor, and the fabrics are cheaper. So now if you compare the cost of the cubic meter of materials with CSEB and fabrics, you have this. This is in terms of cost. CSEB is about 170% kosher today. Before it was like this. And that's why I don't understand the market in Pondy because of this. The fabrics are cheaper than in 2011, when there is 70% inflation rate locally. But, a big but, the country fabrics are produced often by bonded labor. That means slaves. And our workers, they have all EPF, ESI, gratuity fund, insurance, and bonus of Diwali and Pongal. And these bonded labor, they have nothing. They can be fired anytime that people want. And it's not acceptable to have still this in India. That means you cannot compare CSEB and country fabrics because you cannot compare the cost of labor. So now we compare the cost of CSEB and fabrics with the finished wool. So this was only for the material of the wool, just raw material per cubic meter of material. And here we have the wool, either in square meter or cubic meters. The difference is now really interesting because you are cheaper, about 20% cheaper by cubic meter for the finished wool. And why? Because you have less mortar. The blocks are very regular in size. The mortar is, yes, you see, you have 50 to 60% less of mortar inside. That means saving on mortar. We stabilize also with earth, and the mortar is also cheaper by 30% than cement and mortar. Because in terms of strength, our mortar has one cement, 4 soil, 8 sand, and a cement mortar will be in general 1 to 6. And this mortar use will be cheaper by this amount from the cement sand mortar, but the same strength also. Also, we don't need plaster in most of the cases. And you don't need frame structure, you don't need concrete frame. That's why at the end we are so cheap in finished wool. It is very labor-intensive technology. We need in general 13 people per press for the manual pressing. This gives job opportunities with people who want to work, of course. Because sometimes it happens that people, they don't want to work by hand. I had a case once in Ethiopia. People, they did not have the job, but they prefer to chat under the trees, to smoke and to drink than to work. And the project failed because of that. So this can give a livelihood to people, which can ensure sustainability locally. Example of a cost breakup of CSEB, you have here the labor, about almost 37% of labor cost. This is only for the block production. Soil about 30%, cement about 14%, equipment will be much less, 8% or 9%. And when you compare the building with finished with built with vault and domes, you have a totally different figure. You have up to 60 to 65% of the building is labor. If you want to compare with a concrete building, you have the opposite. A concrete building will be about 35% of labor cost, and the rest of cement, steel, and aggregates. And the materials represent 35 to 40% in our case. That means you have concrete buildings, you have the reversed system. And that's why it is much more cost effective, because you spend money with people. That means you give money to people to live with. Because if you want to build with concrete, you have to spend money which go to Mumbai for the steel, to Delhi for whatever, to Madras whatever for something else, or Bangalore for something else. But when you build with us, the money stays locally. That means with people. And that's why it is more sustainable for that. You can promote endogenous development because you have to manage properly the resources locally. So if you manage yourself your site, you can manage properly the resources yourself. These examples of quarries that you have done in Auroville, you have, because if you have something locally done, people can manage themselves their own resources. Examples of quarries, you have underground water tanks here. You have here a reservoir with open tank here. This covers the rainwater which overflow from the tank inside. Rainwater harvesting tanks here, backpack collection, wastewater system here, another wastewater system here, and a basement floor. This basement floor for the apartments of Vikas on 4 floors. In fact, we took the earth from the basement here to build 4 floors above here. That means the building is totally self-sufficient for the soil needs. That means this can be very beneficial if you plan it well, but on the opposite, it can be disastrous if you don't plan it. So if you want to be really sustainable with natural resource management, you have to first plan your quarry in such a way that you can transform it after in such an example. Rainwater tank, rainwater harvesting tanks, wastewater systems, basement floor, swimming pools, or whatever. So now emissions and energy. This is the emissions of CO2 for the manufacture of the building materials in India. You can see this is CSEB on site, if you are produced far away, and fabrics here. So this represents, in terms of emission, this represents 13 times more than this. Initial embodied energy, you have seen that what it is. We don't have to fire the blocks here, we just have to cure them. We have less transportation because the blocks are done on site, and often with a manual machine. Now, if we compare the embodied energy, we have here this much and this much, which is 11.2 times less. And carbon emissions, as we have seen before, they come mostly from cement. But as you have only 5% cement, it's not so much in the block at the end. And this is 13 times less than country foul bricks. Because the 15 tons of wood for the fabrics burns about 79.2 tons of CO2. Examples now of embodied energy for buildings that we have built, like realization on 2 floors on that side here. We have this kind of data, CSEB and stabilizers from the foundation to the roof. Because foundations are done with rounders, stabilized rounders. We have here stabilized rounders with 5% cement inside. And we can build up to 4 floors with this. We have built 2 floors here. As I said, there were 3 floors. We had rainwater harvesting system, wastewater system, which was biological system. We have what we call a geothermal system. Earth tunnel is a geothermal system for air conditioning. It means I will not detail it too much here, but basically you just have to blow air in a pipe. This was here. You just blow in you have a big fan here. You just blow air on the ground in a pipe, which comes up into the building with lower temperature, by 7 degrees lower. Then we have initial embodied energy 4 times less than normal buildings, like a CC frame with a CC slab with infill of bricks. And operating energy 3 times less. And now we finish with that. So this dome was the dome that we used in Riyadh. This was the dome of Almeidi Mosque. So remember, this mosque was built in 7 weeks, from the bottom to the top here. Thank you for your attendance. So now we can have maybe questions if you want.
Thank you very much, sir. It was exciting to see such a large quantity and also variety of work that uses and so many places in which such a technology, it's almost universal, the application of this technology. And I hope this presentation will excite students enough and they come to Auroville and learn, or any other place, and learn this technology and start promoting and utilizing it when they practice and throughout the country, hopefully, and also other places. We have architect P.B.Sajan sir with us. We would like to have a joint panel discussion at the end. I request
Hello,
all the
Sajan.
audience to post their questions in the chat box, either in the Google Meet or in the YouTube link, and we will have a joint panel discussions where both the speakers will address your questions.
Yes, I would like to say also that if students want the presentation, they can have it as a PDF. So please share the presentation to the students if they want.
Yes, sir, most definitely. We'll make it available to the students, so it
Yes.
will be beneficial for them. Thank
Yes.
you, sir. I would now like to welcome P.B.Sajan sir and introduce him. Architect P.B.Sajan sir is an architect by education and practice. He has been trained and mentored by Laurie Baker sir. He is the member secretary of the Board of Governors of LBC, chief architect and joint director at COSTFORD. A committed disciple of Laurie Baker sir, from the beginning of his career, he has been passionately promoting architect Laurie Baker's approach to architecture and building construction through project execution as well as research and dissemination of knowledge in cost-effective technology through policy advocacy and numerous training programs to a diverse group of people, both in India and abroad. Some of his projects include design of over 2,000 residential buildings in different economic ranges, 26 slum rehabilitation projects, many eco-restoration projects, redesign and execution of tribal hamlets, school buildings, campuses, and hospitals. His current focus in research is on using mud and bamboo as an alternative to high energy consuming building materials. With this, we would welcome Sajan sir to our dais and request him to start his presentation.
Thank you, Abhijit, for your elaborate introduction. I would like to talk to Satprem Maini also. Hello, Satprem. Yeah, you are also on mute. I can't hear you.
Yes. Hello, Sajan. Hello.
Yeah. Hope everything is fine there. Hope
Yes.
everything is fine there. Yes, in Pondicherry.
Yes.
Are you in Pondicherry now?
Yes, I am. Yes, in Auroville.
Yeah. Okay.
Yes.
Okay. Yeah. Shall we start our presentation?
Yes, sir, please.
Good morning to all. As Abhijit introduced, I'm architect Sajan, but I have not started as an architect with Laurie Baker. I was a civil engineer. After joining Baker, Laurie Baker only persuaded me to become an architect because I started practicing architecture with him. Then he persuaded me to become an architect, and I studied architecture afterwards and became a member in Council of Architecture. Then I learned architecture from Laurie Baker, not only from him, from on-site work and theory, as well as theory, both club. And mostly my architecture education is like a Gurukula with Baker. I worked with him for 22 years till his passing away from 86 onwards. He passed away in 2007. Actually, can you change the slide? Yeah. I think all of you can see this slide. Because our Abhijit introduced my present current research is on mud and bamboo. The reason for we turned into mud and bamboo is this. 40% of world's total materials and energy use, and also 35% of world's carbon dioxide emission is because, or it is all impact of building industry. This is the reality, and also 16% of freshwater withdrawal. That is also for the building industry. This is all the reason we thought of changing and select bamboo is one of the construction material. And also we don't want to label bamboo as a poor man's building material. Actually, bamboo is a wonderful material, and also we don't want to label it as a poor man's material. It can be make use of anybody, even if it is a economically solid person, or if it is a economically weaker person. Everybody can make use of bamboo as a construction material for their home. This is what we are trying to do now, propagating bamboo in middle class and upper middle class and higher income group housing in Kerala. Actually, it is propagating. There are many good lessons from bamboo. Next slide, please. This is the reason why we are not using cement. Even as a stabilizer also, we don't want to use cement in our construction. Cement is a wonderful material, that is all of us know about it. But we want to reduce the use of cement in our construction sites. 1 ton production of 1 ton of cement will release 0.83 tons of cement, carbon dioxide. You know what is 1 ton of cement? It's just 20 packets of cement. 20 packets of cement will produce 0.83 tons of carbon dioxide. Next slide, please. This is another graph which shows, you can also see, because of this, I have to explain the graph. Actually, this thick line, in this dark thick line, I don't know whether you can see my cursor or not, but on top, the topmost, that thick line shows construction with biomass. Construction with biomass. And these triangular ones are the, in this graph, it shows this is the construction with minerals. And in the bottom line, it is actually year. It starts from 1900 to 2005. This is the graph. And you can see in 1900, the construction with biomass is in very high. And it is slowly growing up. But construction with minerals was very low in 1900. And it crossed in the year 2000, it crossed this construction with biomass and shooting up. All of us are aware of global warming and also, climate change, etc., just because of the carbon emission. All of us are aware of it. And mainly this global warming speed up in the year 2005. One of the reasons for that is this. The reason for why biomass? Biomass, it's either wood or bamboo. These two are in the case of biomass. Earlier, all of us in the world, mostly if wood is available, they will use wood. The main purpose of it is wood will not emit carbon, but it will absorb carbon and sequester that carbon inside the wood. That is what called carbon sequestration. 1 hectare bamboo will sequester 20. There are many studies regarding that. I took the lowest of it. 1 hectare bamboo will sequester 21.41 tons of carbon dioxide in a year. That is what the lowest one. Average, it is actually from a study from China, it shows 60 tons of carbon dioxide in a 1 hectare of bamboo. Means when you produce 20 packets of cement, 0.83 tons of carbon dioxide release. But when you use bamboo, 1 hectare bamboo will sequester 22.21 tons of carbon dioxide in a year. That is the difference. When you construct with the wood or with the bamboo, we are also storing carbon. This is the importance of construction with biomass. This is the reason we started using biomass, especially bamboo, as our primary construction material. The next slide, please. This is the PER, process energy requirement for the material. Cement requires 4.6 megajoule per kilogram. And when you bring down, it's a glass and aluminium on the bottom. Aluminium requires 170 megajoule per kilogram. Next slide, please. It shows little more. Yeah, these two. Cement 4.6 megajoule per kilogram. In situ concrete is 1.9 and steel is 33.3. Glass is 12.7 and aluminium is 170 megajoule per kilogram. I know most of you are not aware of what is megajoule, but you are aware of unit of electricity because all of us are paying charges for electricity in unit, 1 unit. 3.6 megajoule is 1 unit of electricity. That is a conversion. 3.6 megajoule is 1 unit of electricity. And 170 megajoule is required to convert our aluminum ore into proper aluminum material. 170 megajoule per kilogram. All of you know that the sheets which is used by the people in and around world, not only in India, everywhere you can see this. That is called aluminum composite sheet, composite sheets, aluminum composite, ACP sheets, aluminum composite panels. That is what it is called, aluminum composite panel. Aluminum composite panels are using everywhere with all buildings to make the facades. Because it being a composite panel, that panel we cannot even recycle. You cannot, because there are 2 materials already. It will be very, very disastrous after maybe 50 years or 100 years. When they remove that aluminum composite panels, that will become a very, very huge waste in the entire local area. Only the use of that aluminum composite panel, we have to take it to the landfill. We cannot even recycle it. That is the importance of that. That's why I'm insisting aluminum is 170 megajoule per kilogram. Next slide, please. This is the importance of bamboo. It's renewable. Only 3 materials are there in the construction industry which is renewable. One is wood, second is bamboo, third is seashells. Out of seashells, we can make lime, a very good construction material. Only 3 materials: bamboo, wood, and the seashells. None of the other materials, including earth, is not renewable. It is all recyclable or reusable. Many materials, including rock and earth and all, is reusable, but that is not renewable. Bamboo is fast growing. Bamboo will grow in the fastest growing plant in the earth. Sometimes it will grow every day. It will grow 1.5 meter high, 1.5 meter high every one day, and it will mature quickly. After 6 years, we can cut and make use of bamboo for the construction. After 6 years, and different types of bamboo is also available. And also carbon sequestration. 1 hectare of bamboo will store 21.41 tons of carbon dioxide per year. And definitely enhances local job opportunities. Definitely. I will tell you an example. We started using bamboo in our construction, in this construction sector from 2012 onwards. 2012. Till then, it was all in different stages. And in 2012 only we started using bamboo in our construction sector, COSTFORD construction sector. From 2012 until date, we paid 30 lakh rupees in a tribal community. 30 lakh rupees. And we procure bamboo from that, and we completed more than 35 to 40 houses, 35, exactly 38 houses with bamboo and mud. I will show you some of the photograph of the houses also. But we used only that much because we constructed only that much. Now at present the many constructions are going because it is started propagating, and gradually people could see that buildings, and they came to build for themselves. First we have to convince them now. Without convincing them, it will be impossible to build for the mainly for the high income group and middle income group people. Then they have to be convinced. Then only they will construct their houses with bamboo and all. And we started, and actually we completed 38 houses for the different category of people. And we paid 30 lakh rupees to these tribal communities just for cutting of bamboo. And their main job is to cut the bamboo from the forest and carry the bamboo from the forest to the road. And from there, they have to load the bamboo into the truck. These 3 jobs alone, we paid 30 lakh rupees. And that is the importance of this enhanced this local job opportunities. And another important thing is this treatment of bamboo is also can be done by local, and that is another job opportunities for the local people. Next slide, please. This is the IS code for bamboo, Indian Standard Code for Bamboo. Anybody in India can make use of bamboo as a construction material. It is already documented and put in the IS code. You can see the last one, structural design using bamboo. There is also another IS code, IS 15912-2012. That is the structural design using bamboo. This is very important for our architects and engineers, because many people, when I started in 1986 with COSTFORD, the main question about the people, mainly engineers, asked us was whether this technology is included in the IS code or not. That time, filler slab and rat trap bond was not included in the IS code, and we struggled during those days. We started propagating it and all, but we very much struggled during those days. Now it is all included in the filler slab or rat trap bond. Both are included in the IS code. But bamboo is already included in the IS code. Anybody who wanted to use bamboo as a construction material, they can make use of bamboo as a construction material in their sites. Next slide, please. This is local bamboo. We procured from our local forest, local bamboo. This is just 20 kilometers away from Trivandrum city itself. We have tropical forest there, and we paid money to the forest department, and the tribes cut the bamboo and transport it to forest. Next one, please. And we are using bamboo not only for the structure, not only for the building interior and structural work, also for the foundation. This method is, you can see this foundation. Actually, that is a foundation for a middle class family. It was a lady who wanted to build her house, and many houses also we used this. You can see in the foundation, below the foundation, it is waterlogged. waterlogged, and you can also see it is very, very loose soil. Conventionally, when we think about a foundation there, automatically the width of the foundation will go 2 times or 3 times wider than whatever you can see there in the photograph. In the photograph, it is only 1.5 feet, 45 centimeter wide foundation. And if conventionally, if you design the foundation, definitely it will go up to 90 centimeter or 120 centimeter, the width of the foundation, which we don't want to do. Then we decided to use bamboo piling, which will increase the bearing capacity of the soil, which will take more load. In that case itself, we can save 3 times or 4 times of the quantity of rubble. Mainly in Kerala, we are using, for the foundation, we are using random rubble for making the foundation. It's called random rubble masonry. And instead of making the trench width, increasing the trench width, we limited the trench width into 45 centimeters and increased the bearing capacity of the soil by using bamboo as a piling material. That is also very important. It's actually the bamboo is 5 feet long bamboo, and we push the bamboo inside the trench. When the bamboo push it inside, and it is very important not to cut the bamboo on the bottom as a shape. It has to be flat cut on the bottom. Mainly, bamboo will act as a not a load bearing pile but a friction pile. It will act as a friction pile, one thing. Second is, when you push this bamboo inside the soil becomes compact. This is not our technology. It's actually a traditional technology which is used by our ancestors. And most of our backwater area and all, they were using these techniques for a long time. Long time means maybe centuries. And also in England or in Netherlands, this technology was very much popular there in Netherlands, bamboo pile. And not only bamboo, coconut also we can use, or palm trees also we can use as a piling material. When you use a very 5-story, 6-story buildings, or maybe 20-story buildings also, almost all people were using, before introducing this concrete pile in Kerala, we were using bamboo or teak poles or coconut or these palm trees were using as a piling material. Next slide, please. This is the way which we use this bamboo. Next slide, please. See another one. This is actually a 5-story building. This building we constructed in 1998, and in that case, that building we used bamboo as a piling material. This is also having a story. When we talk about this cost effectiveness, I have to tell you that story also. A person who was a Gulf returnee, he made some money from Gulf and he wanted to start a small hotel in near Kovalam in Trivandrum district in Kerala, and he approached us in 1998. That time, Laurie Baker was very much active in the construction industry, but he approached COSTFORD, and we went to the site and have seen the building, have seen the site, which is very close to backwater. Then I told him, because of the CRZ rule was introduced that time. It was introduced in 1991. Because of the CRZ, you will not get the building permit to build it. And we are sorry we cannot build. We are sorry. Then he asked me, if I get the proper permit, will you build for me? Then I told him, yes, we'll do that. Yeah, immediately my response was like that. But the third day, he brought the building permit and showed me. This is the building permit. He bribed our people and managed to get the building permit. Then we were forced to, actually I gave him a word. Then I asked Laurie Baker, Daddy, what to do? I used to call Laurie Baker as a daddy. What to do? Then he told me, yeah, anyway, we have a commitment, we have to do it. Then we went and see the site. When we dig it, then only find out it's a very, very loose watery land there. And it is impossible to build with columns for a 4-story or 3-story or 4-story building without pipe. Then I told him to go to College of Engineering Trivandrum. In Trivandrum there is an engineering college, our oldest engineering college in Kerala, and ask a client to go there and do this soil test. And he did the soil test, and he came up with the soil report and all. It says 49-meter long pile is required. 49-meter long pile. And in 1998, when we estimated it, the cost of the pile alone has come up to 34 lakhs or 35 lakh rupees. And this guy having only 40 lakh rupees with him. Then we told him it's impossible. The pile cost has come up because we want to get rid of him, because it's going to be an illegal building which we don't want to do. But he went back, and after a week he came back again. Then he asked me, "Yes, I heard all of you are doing this bamboo piling, and why don't we try that? Because I don't have money to do the proper piling with this 35 lakh rupees right now. Then if we can go with this bamboo piling, and why don't you try that?" Then I was also puzzling what to do. Then anyway, we had a commitment. We decided to go with this construction of this building with bamboo piling. This is the foundation of that building. You can see in the photograph the water, how much water it is there. The importance of bamboo piling is the bamboo has to be fully immersed in water. It should not be exposed. It should not be exposed from the water. It should be fully immersed in water. And 365 days, not only one season or anything. It has to be that. Otherwise, if the condition is not like that, you cannot use bamboo as a piling material. This is the condition in bamboo. Next slide, please. See, it's actually a 4-storied building. We designed it for 5-story, but presently it is only 4 stories. And because of that, we went for the column beam foundation, column beam structure, and below the column only we did this that much of bamboo there. In one column, below one column, there was 55 bamboo throughout, 55 bamboo, and we cut up to the level of the water and started column from that level. Next slide, please. You can see you can see that below that column, the bamboo. That was the condition. Next slide. This is the building on top of that bamboo piling. It's a 22 years now. Every year we used to go there and see whether any cracks developed on the because underneath this building it is all fully bamboo. And the cost of this building that time in 1998 becomes only 42 lakh rupees total. That is the cost comparison. The piling alone was 35 lakh rupees and another 75 lakh rupees most probably. That itself has come down to 42 lakh rupees. This is the comparison of the cost. Next one, please. Another method of using bamboo as a reinforcement. At present we are trying and we are experimenting with bamboo as a construction material, not as a reinforcement. Actually, as a full, how to completely avoid concrete and steel. That is the present level of our experimentation, and not only experimentation, our way of. I'll show you how we achieved it. This is actually how bamboo can be used as a reinforcement. This is the foundation. Also, you can see in the photograph. From the photograph, you can see that is near the sea. You can see the sea. This is actually a housing for the fishermen in Kollam district in Thankasheri. There's a place called Thankasheri, a fisherman's colony we built there in Thankasheri, and those buildings. And this is also in 1999. This is actually not a traditional method. Laurie Baker brought this up, this type of foundation. Next slide. This is the method of this foundation. The depth of the foundation is only 15 centimeters. You can see in the drawing the total height is 75 centimeters. Actually, 60 centimeters is the basement above the ground level and 15 centimeters only below the ground. And split bamboo we use for the as a reinforcement. And the concrete also used. It's actually a lime cement concrete. Not only cement concrete, lime cement concrete. Because being bamboo as a reinforcement, lime can be used as a binding material. Bamboo cement concrete, it's called combination concrete. And also we used 40 mm metal, 20 mm metal. It's a graded mix, 40 mm metal, 20 mm metal, and also 12 mm metal, mixed with 50% of lime and 50% of cement. That was the ratio we used for the concrete. Because on top of the soil, we cannot even, and also in the near, very close to the seashore with a salty soil there, we cannot use steel as a reinforcement. The advantage of bamboo, it will not corrode and it will stay inside the concrete. That is the advantage of bamboo. Then we decided to go with this bamboo reinforcement, and this foundation is called surface beam foundation. Next slide, please. All these houses, you can see the foundation of each house. Its entire foundation is done with surface beam foundation as a bamboo as a reinforcement inside it. Next one. I am telling you one by one the use of bamboo. The first one is the bamboo piling. You can use bamboo as a piling material. Second is this bamboo as a reinforcement. And incidentally, that bamboo is almost equal, having equal tensile strength as steel, ordinary steel, not the high grade steel, ordinary steel. Both of them having almost equal tensile strength. And this is the one which when we use bamboo, and of course our bamboo piling and as well as in the reinforcement, those bamboo are no need to treat it, because these two bamboo are going to be inside, either in under the soil or maybe inside the concrete. These two insects cannot reach there and they cannot attack. That's why the importance of bamboo has to be fully immersed in water in the bamboo piling scenario. Otherwise, if it is exposed, insects will attack and it will deteriorate. And in the case of this reinforcement also, it will be fully covered with concrete and it will be safe there inside the concrete. And in the case of when we use the bamboo as an exposed one, that bamboo we have to do the treatment. For making treatment, we have as a simplest method we are using. It is called soaking method. Soaking method only we are using for the treatment of bamboo. Bamboo, all its entire of its outer portion, it is water repellent. The water will not penetrate into the bamboo through its skin. It will stop any water or any thing will not enter into the bamboo. For that, we have to make holes in the bamboo to penetrate this chemical into the bamboo. For that, we break the nodes inside the bamboo. Next slide, please. One end, you can see the hole in the bamboo, but that hole will be continuous inside the hole. With the use of a steel rod, we can make the holes from one end, because we always treat bamboo with 20 feet long. That is the length of bamboo which is available from the forest, which is handy to both sides. The entire nodes will be break, because one side it will go to 12 feet, other side also 12 feet. Then we can make sure all the nodes are broken by this steel rod. And we use boric acid and borax as a treating medium. And that is also a 10% solution. 10% solution means if it is total 100 kilogram, 90 kilograms of water means 90 liters of water. and 6 kilograms of borax and 4 kilograms of boric acid. Total it will be 100 kilograms. 90 liters of water, 6 kilograms of borax, 4 kilograms of boric acid. That is the ratio. And the total will be 100 kilogram, and that's why it is called 10% solution. And that is what we are using as a medium for treating bamboo. And these two chemicals are not poisonous. These are chemicals, but not poisonous. If it goes inside ourselves, we will become dehydrated. We have to drink more water. This is what happened into the when the insects attack bamboo too. That not because of the poison, it is all dying. It is because of the dehydration, these insects are dying. When we dip this bamboo into this solution, or if it is a newly cut bamboo, if it is bring it within 1 week, less than 1 week's time, we have to dip this bamboo, or we have to fully immerse this bamboo into this tank for 48 hours. And if it is 10 days, it will, that days we have to increase up to 3 days, 4 days, 5 days. When the time is increasing, the number of days which has to be immersed in water has to be increased. That is very important, because the entire sap content inside the bamboo has to come to this solution through osmosis. And also this chemical will penetrate into this bamboo through this capillary action, also osmosis. These two happens, and entire this chemical will go inside the bamboo. When we take the bamboo from this solution and keep it in a shade, that time our evaporation will happen, and the water inside the bamboo will evaporate, but that will leave the chemical inside the bamboo, and the chemical will remain there inside the bamboo. When an insect attack bamboo, because of the presence of this chemical there, these insects will become dehydrated and die. Very simple. It is not because of the poison it is all dying, just because of the dehydration these insects are dying. And once it is happened, nothing, another set of insects won't attack bamboo too. Then when these insects don't attack bamboo, its life will be more than 75 years. Very simple. Or maybe 100 years. Bamboo's life. Next slide. The preparation of that preservative, it will become a white color, that boric acid and borax. Next. Next. Now I am going to talk about how we can make a bamboo wall or a bamboo skin. All of us are using many methods of having the wall, country burnt bricks or CSEB or any other type of materials we are using for the making of the wall. Here actually, hello, can you hear me?
Yes, sir. Yes, sir,
Actually,
we can hear.
Yeah, some noise is coming, that's why. We decided to do a bamboo building inside our campus, Laurie Baker Center, LBC, Laurie Baker Center in Valapilshala. We decided to start with the bamboo walling and all. And we decided to minimize the material use, and maximize the use of our renewable materials. Then only we decided to do with bamboo. Then we decided to make a bamboo skin. And these walls are not load-bearing walls. Then we decided to make a small column structure. Because main idea is, if you want to make a bamboo house with 1 or 2 stories, we can use bamboo as a material which can taken care of the load of that structure. Or you have to go with laminate bamboo. Laminate bamboo is very, very costly. With the laminated bamboo, we can go up to 30 stories also. That is true, but it is very, very costly. Then we decided to go with very small, thin concrete columns. That concrete columns can be converted into steel columns also, because steel can be converted, or maybe it is reusable later, maybe after the life of that building, after 100 years or 150 years. they can make use of that steel too. Not the concrete cannot use in that way. Then outer bamboo skin. The next slide. Next slide. And the methods are developed in such a way bamboo can be fixed with this column, and bamboo skins are prepared. Outer also. No, only split bamboo we use with the skin, and it is all nut and bolt with total bamboo also, and we just sandwiched it. Inside there will be bamboo skin and one bamboo, and another bamboo is a half bamboo which we use, and these two will be sandwiched in between this skin of the bamboo also. You can see in the photograph. Yeah, next. This is it. All concrete column, but the column sizes are 6 inches by 6 inches. Very small. 15 centimeter by 15 centimeter is the column size. And bamboo is also, because it's actually a composite structure. Bamboo is bolted together with this concrete column. Both the side of the column, there will be one bamboo. And the bamboo has to start from the bottom itself. And that will be a composite column. Next slide. After making this skin outside, we make a wattle and dog. Wattle inside. For that, split bamboo again weave and keep it ready there. Like this is the just made a wattle and keep it there. And next slide. And in just inside that bamboo skin, we put this wattle inside. Inside of it, it is wattle. And next slide. Prepared mud. In this mud, we mixed 50% coir fiber. 50% coir fiber, and thoroughly mixed it. And also we wanted to avoid termites. And also some stabilization is also required. Then we used 10% or 1:10, 10% lime in it. Mixed lime and mud earlier, 3 days before. Then take that lime mud combination and mixed that one with 50%, 1:1, 50% coir fiber, chopped coir fiber, and thoroughly mixed it completely. And we have to prepare this 3 days before. We prepared it 3 days before, and after 3 days only we used in the building. Next slide. And this preparation is also, we can use it either a machine, a concrete mixing machine we can use, or manually we can do it. And we did it manually also. For this building, it was done with manually. Next slide, please. Inside, after putting this wattle inside, we plastered with this wattle and daub from inside. We get a very good finish inside with mud finish, but the thickness of including the skin of the bamboo outside and this wattle and daub, the total thickness of the wall has become only 7 centimeters. Next slide. Yeah, this is the finish inside. Next slide. Its building is coming up. Next slide. That building is coming up. Yeah, next slide. And it's a roof also. This is the roof. You can see a bamboo bolted beams we use. Bamboo beams. Bamboo beams. And also you can see the primary bamboo beam, and also secondary bamboo beam. This is exactly not the same building. This is another building, but the roofing method I want to show you. That's why I just used this photograph. And because in Kerala it is very, very difficult to get a straight bamboo. Maximum we can get 10% bamboo, maybe straight bamboo. The rest of the bamboo all are bent bamboos. Yeah, but for a structure like this, we need to somewhat straight bamboo we require. Then that out of this 10% straight bamboo, we made these beams. And we divided our entire room span up to 1.5 meter, 5 feet. And every 5 feet apart, we placed these bamboo beams. And on top of these beams, we put up the cut bamboos, 1.5 meter cut bamboos we used. Then that bending of bamboo is not an issue in this. In this case, it is there is no issue for that. Then on top of this bamboo, next slide, we used again mud. For the intermediate slab, entire concrete and steel is avoided. Entire concrete is avoided. Only bamboo and mud. On top of the bamboo, again, this mud is also mixed with lime. That is also 10% lime we use. 10% lime. Sometimes it's only 5% lime also used. Now at present, when we do the for this particular building, we use 10%. But right now we are using 5% lime for it, and that is also good. 5% lime is also good, and just level it, because in the bamboo it is all undulating with the surface is like this. Then we level it with this lime mixed with mud. It is that is used for the leveling of the slab. Next slide. This is the look from underneath bamboo. This is a finished slab, and many people like this, and whoever wanted to or whoever liked this bamboo, they like this, others don't like it. That is, we cannot help it with. Yeah, next slide. And also definitely coconut. In Kerala, we have plenty of coconut. In Konkan area also we have lots of coconut. And entire coconut. Earlier, these coconuts were our primary building material. Now nobody is using coconut as a building material. Only coconut use is they are taking coconut to burn these bricks into the brick kiln. They are using for burning bricks, entire coconut. But here we try to make use of coconut as a column or a beam. We can make use of this full trunk coconut as a column. For an example, if it is a 100 feet long coconut, on top of this coconut, lots of coconuts and its a huge trunk is on top. That much weight is taken by this entire coconut. But when you design such a coconut with that much load on top of this 100 feet above, the size of the concrete column will become 1 meter. But this coconut is only 30 centimeters. And because of inside the fiber, when the wind comes, it will sway. The concrete, when you design it is 100 feet long, on top of this 100 feet long, that much weight of this coconut, its size definitely will be 1 meter, diameter. That itself it shows the strength of this coconut. We can make use of coconut as a column. Next slide. Columns. And also coconut, we can use it as a next one. It's a garage, but entire coconuts are used for the structure. That also you can see. 2-story. You can use coconuts as a column. Next one. Bamboo as a opening. Now the bamboo walling is over, roofing is over. Now the opening. All of you know Kerala windows, about windows in temples, which is all wooden, beautifully carved windows, but the sides are open. And you can also see in this this room itself, I used bamboo only for the ventilation. Next slide. See one of the room in our living area, because this room don't need any privacy. In that case, why don't we go for this type of a ventilation, like a bamboo and recycled reapers as a crossbar, or even split bamboo itself, we can use it as a crossbar. Next slide. Another one, casuarina. Casuarina is the use of casuarina is making scaffolding in the building industry. Making scaffolding as a use it outside, and they put up as a scaffolding and make use of. That is the only use of casuarina. But here we converted that casuarina into a major building construction material. Next one. And the treatment is the same. You can see this. Entire rafters we converted into, or we did it with casuarina poles. Treated casuarina poles. Next one. Different areas. And also that ceiling you can see that is also bamboo ply, not any other ply, only bamboo ply we used as a ceiling. And with the same material, now Kerala Bamboo Corporation, we have a government industry, they started making roofing sheets with the same material, corrugated roofing sheets. Actually, on top of this bamboo ply, all joints we make it waterproof because it is possible. Because all the boards in fisherman boat, no, all those boards are made of plywoods, and they make it waterproof. And outer of this our plywood, they make it with fiber sheet. That is how the boards are making. Similarly, only the rainwater, no, or that joints we can make it waterproof, and that will be a proper roof. On top of this, again, on top of this bamboo ply, next slide, we can put up tiles. That tiles also in Kerala, plenty of recycled tiles, tiles from old buildings are available. That is also we can make use of. This is that building which is when we completed, that bamboo skin building, when we completed in Laurie Baker Center. Next slide. Same building. I thought I'll show you some of the different photograph of it. Next slide. Next slide. This is the same method, casuarina, coconut, bamboo, mud structures without using any cement in it. Direct mud. It's a house for a policeman in Trivandrum, in a middle level policeman, not a lowest or highest, but a middle level policeman. His house, he was ready to use bamboo and mud as a construction material for his first house, not the second house, definitely. First house, and he was ready and he wanted to make use of it. Then some portion it is filler slab. The rest of the area, it is all bamboo as an intermediate structure, and also roof is also with casuarina and also bamboo as a. You can see that from the photograph. Next slide. Two houses together. What I am trying to tell you, this is mud and bamboo are important, and also the propagation of this technology is very much important. For the propagation, we have to convince our middle class and upper middle class and high income group people, and don't feel like bamboo or mud is only for the material for the poor people. And actually, this can be make use of our high income group people also. Now, next photograph. This is a same bamboo slabs and recycled materials used, including the bricks. You can see it is all recycled bricks from demolished buildings. It's actually a 3-storied building. One of the architect at COSTFORD made his house with this. This is one of our architects' house. I think he already joined in the webinar here. Next slide. This is a high income group housing. Another one of the MLA, MLA, he made his house with bamboo and mud. He decided to make with bamboo and mud. Next slide. His house is top floor. It's actually having 3 floors. This is the second floor. Next slide. Same house from the other angle view. This is not a farmhouse, proper house. He's living there, but he's having some land around it, some banana plantation and all. Next slide. To start with, I did my house with the bamboo and mud because I don't want to experiment with others' money. Then we decided to do it with our money and show people, because I was that much sure about mud and bamboo is possible. And it is long lasting. This is when we completed this house. This was in 2012. The entire house was visible. You can see it's actually 4-level house, but one point it is only 3 floors. That you can see from this photograph. The next slide, please. Along with the house, our neighborhood and environment is also started growing. There was nothing in our plot. It was a barren land. And after the construction, we started planting of trees there in 2012 itself. Because that is the philosophy which we want to propagate. Not only the mud and bamboo, the environment is important. Environment is very, very important. Without oxygen, now we are all talking about carbon dioxide. Now in China or in Delhi, the oxygen level is very, very low. All of you know that. What is the remedy? Only the remedy is to plant trees, grow trees. Not only planting, grow trees. Next slide. In 2014, slightly started growing. Next slide. 2016, you can see mango, guava, and jackfruit. It is all coming up. Next slide. 17, that is again started growing. This is not Photoshop. I took photographs in these years. Next slide. Now, this is in 2018. And the house means our looking into a building is an ego to our architects. We have to break that. A building, just looking or pointing into a building and telling us, that is my building. That ego, that we have to get rid of. Why? The building has to be seen with the environment, not only the building. The environment is important. The entire. This is what Laurie Baker started propagating, and he practiced it. His buildings are very, very difficult to find from a long distance. If that building will be merged with the nature, Laurie Baker's building, that will not jet out. That's why Laurie Baker always said, we have to break the ego of our architects. Thank you very much for patient listening. And first, we have to reduce the carbon dioxide as well as increase the level of oxygen. This is the only way to do that. Thank you.
Thank you very much, Sajan sir. Wonderful to see your work also in line and exploring a slightly different material from the presentation what we saw below. Weaving as an umbrella for protection from rain. So can it be used in building construction also?
Yes, the coconut leaves were the traditional building material here. This was, for the low-income group housing. People were using coconut leaf weaved together, like and 2 coconut leaves stuck it together and make use of for the walling, and also for the roofing they were using it. Only thing is, after 1 year we have to change it. Every year we have to change it. That is why people are not using it as a proper construction material now. It was possible, and it's very, very cool inside when we use it. And there is during the raining time there is no noise, because that will not have any noise from this coconut leaf roof. My ancestral house was with thatch roof. It is called thatch roof, obviously.
So there is a question. Yes, please, Ritika.
So about if we have to change it every 2 years, so but it is actually very easy to construct it. So if the person who is living there can actually change it after again 2 years, so is that possible?
Yeah, that is possible. Earlier, actually, it is a community life. No, earlier and one person wanted to change his roof, the immediate neighbors will join him, and all of them together change his roof, coconut leaf roof, thatch roofing. Every year they will, the next time they will go to the next person's house and they change it. The next person, and that person will make a sadhya there in his house. For that day, everybody will go there and have food from his home. There is no wages, only this food. And that is how in Kerala they were doing earlier. Now it is all sidelined, you know. That's why coconut was the main important building material, including everything they were using for the making the broom. They used these coconut sticks. Everything was used for this from this coconut trunk, and sawn trunks were used as a rafters, and the reapers they made it from the coconut itself, sawn reapers, and it was all hand drawn. There is no machine available during those days. It's all hand drawn, and so on.
I also heard that if we use some chemicals on this, like if we use some chemicals,
we did some. Yes. Sorry, interrupt. Sorry, continue.
No, I read somewhere if we use some amount of chemicals, I don't know the name of it, so it can last up to 10 years, this roofing or material.
Yeah, actually we experimented with coconut thatch earlier. In 90s, early 90s, we experimented with Laurie Baker's time itself. And we used, Turisha. It is called copper sulfate. Copper sulfate mixed in water. 100 liters of water, we mixed 3 kilograms of copper sulfate and dip this coconut leaf inside it and keep it there for 4 or 5 days. Then only we used it. That lasts for 3 years, not 10 years. That lasted 3 years. And after 3 years, we have to change it.
So there is a question: can we use shell lime as a stabilizer in CSEB? If so, what is the percentage? And also how waterproofing is done in CSEB vaults and domes with mud mortar?
Okay, so first I will start with the last question with the CSEB waterproofing for CSEB. In fact, I have shown some photos of vaults with the CSEB with earth plaster for the waterproofing. This was research, but we don't implement it now because it can work with only some local material from Auroville and Pondicherry, and also it does not last almost 5 years. After 5 years, the roof starts to leak because we use lime. In fact, we use little cement for the strength of the mortar, but mostly the waterproofing is based on lime, local lime from Auroville, from around Auroville, with some soil and katukai and patikaram. Patikaram is alum that you find in Pondicherry. And the problem is that this material, the patikaram and katukai, they get destroyed by the sun after some time. So we have done some more research on it, and we protect this waterproofing with something different, with another plaster. But we did not go on with this research because for this, you can test this kind of principles only for actual buildings. You cannot do research in the lab because you have to be exposed to the sun, to the rain, to the hot, to the cold, and this and that. But what we do now, we have in general a cement plaster with ceramic tiles. It's not really green as a material, not really ecological, but I don't have really solution. And for the use of shell lime, yes, we use shell lime, but mostly for plasters. Because the problem in Kerala, you have a lot of shell lime, not in Auroville and Tamil Nadu. We get sometimes shell lime from Kudalore, which is south of Pondicherry, about 40 kilometers from our place. And we use shell lime only for plasters, not for CSEB because it will cost too much. Because if you want to put lime, instead of 5% cement, I may have to put 8% of lime. And first, lime costs 3 times more than cement by kg. Because shell lime from Kudalore, you have to go to buy it, and you have to hydrate the lime. You have to be sure that the lime was not too old. And at the end, the cost of lime per kilo is 3 times more than cement. That's why I would love to use lime as much as I can, but I cannot afford. In Kerala, you might. Because Kerala, you have much more shell lime. Maybe it can be much cheaper in Kerala. That's why Sajan used, I think, shell lime. But we cannot here. It's too expensive. But it can be done.
Sir, this question is to both the speaker. So, what are your opinion regarding LEED and GRIA? What kind of certificate they give, and whether they are really green? They produce green architecture, because when I see, they can also give certificate to a aluminum composite building when they fulfill all their norms, but actually they are not green buildings. So, what are your opinion regarding following LEED and GRIA norms?
Okay, Sajan, you start or I start?
You start, I will follow. I will fulfill.
Okay, in fact, you see, I started my presentation with this example. In fact, I have many presentations, but I selected only one slide on that. I have a bigger one for embodied energy. I don't consider at all these buildings green. They have this label: green building, leads platinum, bleeds gold metal, and blah blah blah. And you have how many tons of energy inside, how many tons of carbon dioxide emitted for the construction of it, and the least energy consumes the building for the operation, the more percentage increase for the embodied energy. When I mentioned 30% of embodied energy for the construction of the building for the lifetime, it is on a commercial building. But if you have a LEED certified building which consumes much less energy, maybe this energy embodied can be up to 50%. And this is not peanuts at the end. But if you can save on one side for the embodied energy and then further for the operation energy, then you win. That's not what they do. That was CSEB compared to bamboo. I know that we emit much more than bamboo, of course, because even if you emit 11.2 times less than country fabrics, I'm sure we emit 100 times more than bamboo. Bamboo is sequestering carbon. Bamboo does not emit, bamboo saves carbon. That's why at the end we consume more energy and carbon emission with CSEB, but bamboo is the best for that. Or raw earth. If you build with raw earth, then you have zero emissions. But advantage, bamboo is minus emission because the bamboo takes carbon from the atmosphere. So Sajan, if you can go on.
Yeah. Actually, some of the buildings, they are saying that because of they are producing energy through solar and maybe some rainwater harvesting or recharging situation, they are putting up with the green certificate and all. But when you compare with the in situ energy or the energy used by these materials and the process energy for that material, when you calculate it, the saving energy is very, very, very limited, very, very small percentage. For example, one of the calculation in one of our building, what we saved, if you are using a 300 unit of electricity in a month, when we calculate the savings of energy, which when we compare with the process energy requirement, it is nearly 180 years. 180 years of that much of energy we saved for converting that building into this bamboo and mud. That is the calculation. And saving a small amount of energy and putting that building in a green building category or a green certificate is rubbish. And they are doing that way. Actually, they have to calculate the entire energy consumed by that material, by that building. Then only they have to put in that building into that category, whether it should be in green category or not. Or how can we certify a building which is using this aluminum composite panel as a facade material? It's rubbish.
Yes, sir, and they use this certificate to buy TDS and they sell it to the developing country also. Like,
yeah, they are getting money.
yeah,
And all this green business is business. It's a green business. Yes. And they are saying you have to change your fans with the new fans. Then they can sell one product, no?
Yeah.
Their extra product. and they have to use change everything into that is good when you use LED bulbs and all, which consume less energy, which is good. I'm not saying that is bad, but alone that is not proper.
Yes, sir.
So we have been looking at both your projects, which cater to all kinds of clientele, right from schools which are in rural areas to some of the clients who are fairly well-to-do. Can you roughly tell us, based in Mumbai, we calculate about 1,500 rupees per square feet of construction cost. What would be the construction cost in the case of the technology that you use? Because that becomes a very important factor to convince clients also to use technologies.
In Mumbai, your question is to me or to Satprem?
To both of you, sir.
Okay. Actually, I'll start Satprem for this question.
Yes.
Yesterday, you had this Malak Singh's presentation there. You had it. Malak Singh, he trained here with us. He worked with me here in Trivandrum for 2 years. Then only he shifted to Mumbai and started his practice there. Actually, he is well to do there. He is doing good work in Mumbai, along with our philosophy, as I mentioned about Baker philosophy and all. I think we can save almost 35% of cost. In Trivandrum, we are saving up to 50%, because when I did my house with bamboo and mud, that time in Kerala construction cost is in higher side, not like in Mumbai and other places. Here today's mason's charge is 1,100 rupees. One mason is getting 1,100 rupees a day. That is the level of labor charge. And the helper, ordinary helper, unskilled labor, those people are getting 900 rupees a day here in Kerala. But in Mumbai, that must be 400 or 500 maximum, unskilled labor. And during 2012 in Kerala, our ordinary building construction cost was 1,500 rupees per square feet. During that time, I did my house with bamboo and mud. The first comparison of that cost, because this is the first, my house is the first bamboo and mud building. Mud building we earlier also we did, but bamboo building was the first. And their roof was with bamboo. And its cost was 750 rupees per square feet. That is almost 50%. That is the comparison. That the same thing you can do when you go there and do it in Mumbai. Definitely it will be more, because we require more labor than like unskilled labor than skilled labor. Unskilled labor will be more when you construct with bamboo. For a very, very small training, people can start making this bamboo treatment and all. Very, very small training is required, and unskilled people can do it. And that is the cost. When you use more unskilled labor there, the cost you can reduce more than 50% itself in Mumbai. Only thing is, now at present we are going to start our COSTFORD's own office building. It's going to be a 6-storied building where we are using load-bearing columns or are with steel frames and bamboo. That is all definitely a composite structure with the walls will be bamboo, floors will be bamboo, and slabs will be bamboo. And we are going to provide 2 parking floors with bamboo. We deliberately wanted to make that parking slab also with bamboo, but the columns will be with steel columns. And if the span is more, there also will use steel as a beam. Definitely will be with a combination. And small beams will be with bamboo, but the big beams will be with iron, steel. That is also we just started. Next year, maybe you can see that also. It's a 6-story building. It's going to be a 6-story building. Because the main question is people are asking whether you are talking about bamboo and mud, and time being the space is very limited. we have to go for multi-storied building. And is it possible to build with bamboo for a multi-storied building? That's why we are experimenting with that line. In Kerala, space is very limited now. In Kerala, when you compare with any other state, Kerala is very, very congested. Then we have to go for looking for the multiple story buildings. Then we have to adopt this technology. How it is possible we have to adopt this along with that.
I would say that today we are very expensive in Auroville. What we do ourselves is very expensive, and mostly because of the labor cost. You see, so our masons are more or less slightly higher than what Sajan, and labor is more or less the same, like you said. And when you build a dome, you need more labor. That means the materials themselves, they cost what, about 30% for the building itself. When I mentioned before, the 65% of the building cost for the labor, and there was 35% for the materials. The earth blocks itself is maybe 10% of the cost of the building, and the rest is 65% of labor, and then 20% of industrial products. That's why building a dome costs more today because of the labor cost. That's why I'm not really economical these days, and I don't know how to solve it because I cannot cut the wages of my workers. They work with us since for them 28, 29 years. I have to keep them and pay them this amount. But then it's always a choice, you see. Do you pay materials which are expensive and they come from Mumbai, they come from Chennai or Delhi, or you pay the local labor? I don't mind to be more expensive, the client knows that, but at least the money stays here.
There's a question from Ritika Lalan. Hello, sir. What are your thoughts on green eco-cities that are going to be constructed in the future and their concept of being sustainable?
Yeah, it's actually green cities. Why I explained why we decided to propagate bamboo. The main issue is whether it is renewable or not. If it is a material which is not renewable, how can we call that material as a sustainable material? Once when we use it, it is getting reduced. Then how can we call that one as a sustainable material? Only the material which is renewable, which we can plant, and after 6 years or 7 years we can make use of it, that material. Then only that material only we can call as a pakka sustainable material, right? and that material, the lifespan of that material, if we can make increase very much into maybe 100 years, 200 years, 300 years, then only that material, that renewable material can be called, or proper green can call in that way. And most of our carbon can be sequestered and stored in these buildings, which will reduce the carbon level of our atmosphere. And the main disaster is going to come because of our global warming as well as carbon emission. Kerala is already experienced last 2 years, consecutive 2 years flood, just because of the climate change and because of this carbon emission. And if it is continuous, then everywhere it will be there. In Mumbai, frequent flooding, I know. And in Chennai, we had a great flood in 2014. And tsunami, I don't think of because of the carbon emission, but definitely this flood and things are because of this climate change, definitely. And only answer to all these natural calamities and all is to go for green, not lead green or green, proper green. Then only there, and you can also identify many jobs with the green jobs and other jobs. And that entire of our things has to be changed. Our attitude has to be changed. This generation has to take a lead to change the attitude of our fellow beings. Then only that green cities are possible. As Mahatma's, our Rashtrapida's greed and need, This comparison of greed and need, the same thing. Go back to Mahatma.
So for me, green cities, in fact, I will link that also with this concept of smart cities. I don't know if you heard this program in India of smart cities. And this is total nonsense for me, because what they call smart is very sophisticated systems with management of this, management of that, but they don't solve the main problems, which is what kind of materials are you using. For example, if I want to use earth at the most, I can, because I take the earth from the side. You have seen that all the buildings that you have seen on my photos, the earth was taken from the side. That means we just do holes. We plan the hole to be converted later for wastewater system, for rainwater harvesting system, for basement floor. That means all the earth came from the site itself. And now I'm just doing a small building near Auroville. I could not transport one truck of resol because there is a ban on resol in Tamil Nadu and Pondicherry. What I did simply was to enlarge a percolation pit to harvest rainwater, and then I have the earth for my building finished. You see, and that's why you have to think what to take the resource from, what to do from them to transport them the minimum you can, and that's it. And this is for me the way forward, to have the local resources used locally and transformed locally by people. And this is the way for me for the green cities.
So right now, that's not a problem, but in future, since soil is also, or a mud is also a non-renewable resource, like if we compare with its making, like it takes thousands of years to produce a soil from a stone. So it is also non-renewable as such. But if we keep on using more of a soil, won't it disturb the ecosystem?
Yes and no. That's just a good question, because I don't really have an answer for that, to be honest. But I would say the answer that I have for the aspect of sustainability, I took the earth from the site that I had built. And if you go to this site, if you could visit sometimes today, yes, you will see sometimes the big depressions where we harvest rainwater, but at the end, everything has been totally matched with the landscape. It means you don't see a big hole somewhere which is ugly with garbage inside and waste. You see nice lawns with nice percolation depression, sometimes some trees here and there. It's totally integrated in nature. It means it's always a problem on how you deal with the resources. If you just dig a hole and leave it behind you, it will be filled with waste. And people, they don't care of it. You have so many examples in Pondicherry, but not on our sites. But I would say on a very large scale development, I cannot answer that. If everybody wants to build with us tomorrow, I don't know how we can do it, honestly. Unless if everybody can deal with the soil from their site only, then it can be sustainable and it can be perenne. Not if you have to bring the soil from somewhere else. At least for cities, I'm not sure that building with us is really an answer for big cities, because you cannot take the soil from the city itself. You have to transport from somewhere else. And unless it is managed properly by the city, because every city needs wastewater treatment, every city needs rainwater harvesting. It means if it is planned on the level of the city, it could be done on a larger scale. But always, problem if people are aware of what to do and how to do it. And people in general, they don't care. Example, in Pondicherry, the French, when they were there, they have done a big lake, Pondicherry Lake. There was a small stream of a very small river coming to Pondicherry. They have done a big dam to stop this water, and it's a very huge lake now. And the Pondicherry government, in fact, the Pondicherry government, the Tamil Nadu government, dig a big hole near the lake to take earth for making roads. Later, people came in to put waste, and now this hole is a garbage dump of Pondicherry, which is at 1 kilometer from the lake. It is possible and tremendous danger to have pollution from the waste of the garbage to the lake, which is the main water source of Pondicherry. Yes. Totally mismanagement of resources. On one side, you do a big hole which is not managed. You put dump inside with waste, organic waste, not garbage like rubbles of masonry, but waste of the Pondicherry market and so on, which can contaminate the water table, which is just at 1 kilometer from there. In that case, it's really a disaster. But if you can manage it well, it can be the opposite.
Yes. Yes.
Yes. Thank you,
So,
both our speakers, Satprem sir and Sajan sir, for this wonderful discussion that followed. Also, many of the questions were very well answered, and I'm sure the audience were thrilled to hear from both of you. We would like to thank you both for coming to our webinar and taking time from your schedule on this Saturday, beautiful Saturday morning, and spending time with us so that we can learn something from both of you. I would also like to thank VESCO management, Swami Vivekanand College management, our principal, architect Anand Achari, and all the professors who have contributed their time and effort to organizing this event, the whole webinar 4, which comes to an end with these 2 lectures today. Thank you, all of you. Thank you, both our speakers. Thank you to all the speakers who gave us such enlightening talks in the previous 2 days. And we hope to continue our engagement with all of you speakers in times post-COVID. We would like to come to your institutes and learn more, and the students could learn more from you. Maybe you could come and have some workshops with us, and we would love to invite you to our college also. Thank you very much, both of you.
Thank you.
Thank you. Yes, thank you.
thank you, sir. Thank you.
Thank you to all the participants who made this event very successful. We now formally declare a close of this webinar 4.0.